So the perpendicular bisector, we talked about this yesterday in class. The perpendicular bisector has to be perpendicular, meaning like they have that 90-degree right angle. And it bisects, so that means it cuts the segment into two congruent parts. Or two congruent segments. So there's a couple of pictures here. For this first one, PQ bisects segment AB, but is that perpendicular to that segment? No. But in this one here, it's perpendicular and it's bisecting. So slightly different. Perpendicular bisector has to do both of those two things. So because of that, we have this perpendicular bisector theorem. And the perpendicular bisector theorem says if you have a point anywhere on that perpendicular bisector, so like in this case here, we have point C. Anyone want to take any guesses as to maybe what you would know about these triangles that are formed or that point compared to this line segment? Sam? So the distance from A to C will be the same as the distance from B to C. The reason this is because these are two congruent triangles, and those are corresponding parts of congruent triangles, and that's going to make them congruent. So the perpendicular bisector theorem says any point on the perpendicular bisector is equidistant, meaning like the same distance from the endpoints of the segment. So for this case here, I can say that AC is congruent to BC. And then the converse of that perpendicular bisector theorem would say that if you know that these 2 points are the same distance away from a point, you know that that like C would be on the perpendicular bisector. Okay, the triangles that we folded yesterday, a lot of them you had part of this where this just kind of goes through the middle. You could still have, you know, a point here equidistant to those two endpoints. So you don't have to feel like, you know, well, this doesn't go through point Z, therefore it can't be the perpendicular bisector. It still can be. It's just saying any point on there is going to be equidistant from these two endpoints of that segment.
When looking at this example here, we have WX to be 25.3. We have YZ to be 22.4 and WZ to be 25.3. So even if these congruency marks weren't on there, or if this angle weren't marked as perpendicular, we would still know that these two portions have to be congruent. Because W is the same distance away, that makes it on the perpendicular bisector. So because YZ is 22.4, I would also know that XY is 22.4. So you could go ahead and write that over here for that one.
For the next one, it says if M is the perpendicular bisector and WZ, so this is 14.9, find WX. Well, what do you know about these two parts? WZ and WX are congruent. So this piece here would also be 14.9. So hopefully this just kind of makes sense. You can see these triangles are congruent. The corresponding parts are congruent also. And then for this last one, it says if M is the perpendicular bisector and WX is 4A minus 15 and WZ is A plus 12, it wants us to find WX. Notice it doesn't just say find A, it wants us to find A and then plug it back in. Well, because these two parts are congruent, I can just set 4A minus 15 equal to A plus 12, and I can solve that for A. So go ahead and take a second to solve for A. A should equal 9, and then what do I have to do to find WX? Plug it back in. So plug it back in. You could really plug it back into either spot because they are going to be the same. When you plug that back in, you should get, anyone have it yet? 21. So just make sure you're paying close attention to, like, are they asking you to find the variable, or are they wanting you to do both, or plug it back in and answer the correct question. Okay, yesterday we talked about point of concurrency. Point of concurrency is just the place where the lines intersect. And yesterday when we folded the triangles, we looked at some of this and the location of the point of concurrency. So for this triangle here, these are all perpendicular bisectors. That point of concurrency, we called that the circumcenter, and that's what it's called when you have the perpendicular bisectors all come together. For this one here, for this right triangle, those perpendicular bisectors all come together at one singular point also. I showed you yesterday with the obtuse triangle how they didn't all intersect inside the triangle, but if I were to extend those lines, they would intersect outside of the triangle. So we have that going on. So let me just go ahead and scroll down here. Here's where we're going to put it into our notes. So the perpendicular bisectors of a triangle intersect at a point called the, what was it called? Circumcenter. And the circumcenter is equal distance from the vertices of the triangle. I measured that out for you yesterday. If I go back to this and I measure the distance from the circumcenter to each vertex, here it's like 14.8 centimeters. If I go here and measure, this is about 14.8 centimeters. And this one here should be what? 14.8 centimeters. That point of concurrency, that circumcenter, is equal distance from every single vertex of that triangle. Can't see all those. Every single vertex of that triangle. Same thing here. If I were to measure from there to the vertex, there to there, and there to there, those are all the exact same distance. Can you guys kind of see that? Even when I just take this and spin it around. Okay, so that point of concurrency is equal distance from every vertex of the triangle. Okay, so in this picture here, we can add in, if P is the circumcenter, then it's A to P, it's B to P, and it's C to P, are all congruent. Those are all going to be the same length. Okay, and what you could do is you could actually take this, and I don't have a compass tool on here, but if I did have a compass tool, you could take this and you could, it's called circumscribe that triangle. You could draw a circle around that triangle, because that radius would be the same. I know this looks horrible, but can you guys kind of picture a circle going around that triangle? Because all of those distances would be like radii of that circle, and those are all the same distance. Okay, the next one, the angle bisectors. We've talked about angle bisectors before. If you just need a quick review, the angle bisector bisects an angle. You have two congruent angles. So the angle bisector theorem says that if a point is on the angle bisector, then it is equidistant to the sides of the angle. And when we folded these, that's how we folded them. We folded the sides of the triangle together, the sides of the angle, to find that exact middle point. The converse of this is also true. If you know a point is equidistant from the sides of a triangle or sides of an angle, you know that it's on the angle bisector. One thing I do want to point out for this is you have to have little right angle symbols here because it needs to be the shortest distance. You can't say that like this distance is the same as, this distance here, because then you could have like something very close to one side and then you just draw it a longer way or a shorter way. So they need to be that exact same distance perpendicular, the shortest distance. That should be a little better, right? Okay, so for this one here, you know that this is the angle bisector. You have these congruency marks here. So because this is the angle bisector, every point on here is equidistant to the sides of the angle. So to find the length of DB, you would just say that that's 5 because these parts are congruent. For part B, do you notice that these are congruent? WZ is congruent to WX. So because those are the same distance, that lets you know that this is the angle bisector. And if this is the angle bisector, then both of those angles are 28 degrees. Just pay close attention to the angle that they want you to find. In this case, they want you to find WYZ. So that's just this part. So the answer would be 28 degrees. The question could ask about angle XYZ. And if the question asks that, what would you have to do? Just add the 28 and the 28. So just pay close attention to like the question that's being asked so you're answering the right thing. And then for this last one, these angles are congruent. They're marked congruent down there. So that's going to make these the same distance. Technically, they should have had little right angle symbols in there. Sometimes the authors of the book got a little lazy with that though. So I'm going to set those two things equal. Solving for x, you should get x to equal 3. And then how would you find the length of QS? Just plug it back in. So 4 times 3 minus 1, the final answer would be 11. So any problems or questions with those? Again, hopefully this stuff, most of it is hopefully pretty easy. A lot of things are just equal. The harder part, I think, is when you get to the triangles and you're trying to apply it to, what parts in the triangle are congruent. So lastly, the in-center theorem says the angle bisectors intersect at a point called the in-center. We already wrote that down on our triangles, and that is equal distance from the sides of the triangle. Maybe you want to make a big note of that. I should have had it fill in the blank here. I guess I forgot to get rid of that. But that makes point P the in-center, and that's equal distance from every side. So that's going to make all of these distances here the same. Hopefully you can tell that this is not the same thing as the circumcenter. Is P the same distance from every vertex of every angle? Not even close. Once in a while, if it's an acute equilateral triangle, they will be the same point, but most of the time they are not the same point. Okay, so let's go back to these triangles. Let's go back to the document camera. Can you guys see here, this point is the same distance to every side? If I were to measure like straight to the side, not necessarily straight along this line, but like the straightest shortest distance to that side and to this side and to this side, those are all 4 centimeters. Okay, or if I get another triangle for this right triangle, you're measuring the shortest distance. This is 5 centimeters. If I go this way, okay, this is 5 centimeters. And if I go this way, we have 5 centimeters as well. That one looks a little more. This is probably just folded a little bit off, or when it might be because of this angle here. Okay, or if I do my obtuse triangle, all of these are the same distance to the sides. Notice I'm not measuring this distance, I'm measuring that shortest perpendicular distance to that side when I'm, whoops, that's a little bit off, when I'm measuring that. Okay, and you guys see that those are equal distance to every side of that triangle. So looking at it here, what distances are the same from this in-center? Where are the 3 parts that are congruent? From K, from L, and from J. So all of these parts here are the same. And because this is the in-center, all of these are angle bisectors. So all of these angles here are the same. So the first one wants me to find the length of PK. I have a little bit of a problem because I don't have the length of PK. I also don't have the length of either of those other 2 parts that it's supposed to be congruent to. Here's what I do have. I have that this is 12 and this part's 20. And then what type of triangle is this? A right triangle. How could I find this length here if that's part of a right triangle? I'll draw it separately. Maybe that'll help you see it better. How could I find that piece there? The Pythagorean theorem. Can I use the Pythagorean theorem to find the side of that right triangle? Yeah. So I'm going to set this up. Remember, the Pythagorean theorem says a squared plus b squared equals c squared. So a and b have to be the 2 legs. So that's going to be like x squared plus 12 squared equals 20 squared. So I'm going to solve this. So x squared plus 144 equals 20 squared is 400. I can subtract 144 from each side. So x squared equals, it's going to be 256. And when I take the square root of that, what do you get? 16. So it's not drawn to scale very well. And again, pictures don't always have to be drawn to scale, so don't worry about that. If PJ is 16, then how long is PK? 16 also, because the in-center is equal distance from all of those sides of that triangle. PL is also 16, they just didn't ask me about that one. Okay, and then the second piece here, I want to find the measure of LZP. So the measure of angle LZP is here. This is not 20 degrees because that's the length of this part here. Here's how I do this one. I would look at the big triangle, the whole big triangle. How many degrees is this angle for the whole thing? 62, because 1/2 of it's 31, so you could double that. How many degrees is this whole angle here by angle Y? 54, because this half is 27, so I could just double that to get 54. How could I find the measure of this whole angle here? Okay, so 180 minus, when I add those 2 up, I get 116. So when I add those 2 up, I get 116. I subtract that, so that's 64. So then how many degrees would this piece be? If this whole angle is 64, I can just divide that by 2. This angle is 32 degrees. So make whatever notes you need to on your paper so you remember how to do this. I'd say this is probably going to be like the hardest example where they give you the triangle and you have the in-center. Hopefully everything else within this aspect isn't too bad. Okay, so